I happen to live in Northern California, and a favorite airport to visit is at South Lake Tahoe. Field elevation is 6264 MSL, and the airport is located in a box canyon with surrounding mountains of about 10,000 feet elevation. If you have to depart on runway 18, it requires a 180-degree turn to downwind to exit the airport. Historically, there have been a number of what appear to be departure stalls at that airport. The local FSDO always seems to talk about this every year at one of their local safety meetings. The problem is always attributed to high-density altitude operations and its impact on aircraft performance, all of which are true. However, I've always thought there may be other factors involved that periodically makes a marginal situation catastrophic. We all assume that the associated degraded aircraft performance, coupled with the probability that the pilot gets too focused on the turn while avoiding the mountains and drops his airspeed out of his instrument cross-check, and before you know it, you have a stall. Because we're climbing out at max power, we also know we have to control airspeed in the climb with pitch only. I decided to perform an energy analysis to see if it would offer any other possibilities for causation. I focused on the period between the start and end of turn to downwind. I had to write a computer program, which is an energy state algorithm, to be able to handle all the calculations required. The program essentially calculates the energy states of an aircraft every second and the energy required to maintain a true airspeed. Starting parameters are weight of aircraft, the climb speed, the rate of climb that results from climbing at the climb speed at max power, the altitude at which the turn to downwind commences, the bank angle to be used in the turn, the wind speed, and direction. The program generates a chart of VVI and altitude, kinetic energy plots, and a ground track. Most pilots assume that once an aircraft breaks ground, it now is flying in the air mass and that the aerodynamic performance is solely a function of its relative wind in the air mass. One would be correct in that assumption. However, there are some engineering problems that can only be solved with an energy analysis. This situation is one of those problems. Total energy equals kinetic energy plus potential energy. The reference system for an energy analysis is the ground. Kinetic energy is determined from ground speed, not airspeed in the air mass. We must remind ourselves that the sole source of energy from an airplane comes from its engine. The impulse from the wind is negligible compared to that of the engine, contrary to common opinion. Since turns out of the pattern are limited in duration, both time and altitude, the horsepower of the engine is assumed to be constant through the climb to downwind. Pilots are well aware of the impacts of energy on aircraft performance. Takeoff distance is a prime example. Kinetic energy is 1/2 times the weight divided by gravity times VGS squared, where VGS is ground speed. The kinetic energy of an airplane with a strong headwind component is much less than a no-wind or tailwind situation. The ground speed equals the TAS plus or minus the wind component. That energy only comes from the engine. The aircraft needs true airspeed to fly, but it needs the energy to reach that true airspeed. Note, once the aircraft departs ground effect, the airplane sees the same relative air mass, whether in a moving air mass or calm day. The air mass has no effect on the aerodynamic performance once the airplane takes off. It only affects the ground track. Problems can occur when the air mass speed and direction vector change rapidly in relation to the aircraft true airspeed vector. Specifically, this is when the air mass vector changes and there is not enough kinetic energy available to accelerate it to the required TAS. This phenomena is most pronounced in wind shears on approach, but also occurs during turns in the pattern, or any turn for that matter. The larger the change in the air mass vector relative to the true airspeed vector, the larger the kinetic energy deficit will be. Let's look at a hypothetical. You're climbing at max power, maintaining V sub x at 500 feet per minute on runway heading to your 500-foot AGL turn point. There is a strong wind strong headwind component, everything looks good. You roll into your 30-degree bank turn. You know you have to control speed with pitch. You immediately notice that your airspeed is starting to fall off, which is expected in any turn. So you lower the nose a little to maintain V sub x. VVI will drop slightly due to the horsepower required to maintain the turn. Everything is okay, but you glance at your VVI a moment or two later and suddenly notice a big drop in VVI while maintaining your V sub x. You instinctively think you should be climbing at the VVI that you first noticed when you first initiated your turn. You quickly ask yourself what is going on. Am I caught in a downdraft? Your first instinct would probably be to pull up, at which point you may rapidly enter a stall depending on how great your kinetic energy deficit is. If you did enter a stall, you are already at max power, so you must trade altitude for airspeed to recover. However, there is very little altitude to trade for airspeed in the pattern. Note the VVI values reported by the energy state algorithm are instantaneous rates. To bring the reality of this situation home, I went through the NTSB crash database looking for a departure stall that fits this scenario. I found LAX 00FA.322. Appendix 1 is an extract from the report. A 4,351-pound aircraft departs runway 18 with winds at 170 at 14 knots. Its estimated climb performance is 1,095 feet per minute. V sub x is 90 knots. I don't know about you, but these numbers would have looked adequate to me as a pilot. The pilot departed and started a left turn to downwind at 50 feet AG and a better than 45-degree bank turn. The aircraft appeared to stall about 3/4 away around the turn in about a 90-degree bank, resulting in a fatal impact. Below is a tabulation of the estimated performance for this situation and data on the crash environment as generated by the algorithm. This is the user interface for the energy state algorithm, and as you can see, it's pretty straightforward. What we see here is the first part of the text output from the computer program, and it basically takes all the information we've entered into that user interface, translates it into engineering units, and it also calculates the initial starting point of the aircraft at the start of the turn. This plot of altitude and VVI has got to be really scary from a pilot's perspective. We started the turn with 500 feet per minute rate of climb. We know that. And we can see that it rapidly deteriorates down to minus 134 feet per minute. And the altitude throughout the turn remains relatively constant. This chart shows us our energy states. The red line is total energy, and you can see it's a straight line. It starts from the beginning of the turn and goes straight line till the turn is completed. And that represents basically the horsepower output of the engine, which is constant. So that line should be perfectly straight. The blue line represents the kinetic energy. And we can see the kinetic energy just keeps climbing. And you go, wait a minute, we're climbing at a constant V sub x. Why is the kinetic energy going up? Well, the kinetic energy is going up because the actual ground speed of the airplane, as opposed to the indicated airspeed, has to constantly keep increasing. And it is constantly increasing because of the change in the winds. And we see the green line, and that directly tracks the altitude of the airplane that we saw in the prior chart perfectly, because that's what potential energy is, merely the altitude of the airplane times its weight. Finally, this is the ground plot, or the ground track of the airplane as it completes the turn. As you can see, the ground track is distorted just as you'd expect it to with a strong headwind component, and the values are in feet. This is a view of the airport generated on Google Earth, And you can see where the windsock is, where the liftoff point is, where the terminal, and where the actual crash site is. And these are all referenced in the accident report. This is a ground view near the runway looking directly at the crash site, which you can see is up on top of a little knoll. This is a altitude profile taken from the runway to the crash site, perpendicular to the runway. And the shaded area is the full length of Sumat Street, which is very near where the aircraft crashed and is referenced in the NTSB report. This is a topo map of the crash site. The blue flag is right at the end of Sumat Street. This is an elevation profile for the complete length of the Sumat Street, which is where the aircraft crashed. The red track shows the ground track for the aircraft in the turn, and at the bottom you have a relief map for that exact ground track, and the shaded area is the length of Sumat Street, so you can see where it actually crashed and how it got there. The distance from the runway centerline to the crash site is 2,600 feet. The elevation crash site is 6,430 feet. There are 75-foot trees in the vicinity. This makes the total obstacle height at about 6,500 feet in the crash area. The crash occurs 23 seconds into flight at an elevation of 6,430 feet. The predicted altitude from the algorithm is 6,355, which means the aircraft crashed. This analysis supposes that he did not maintain enough Gs for a coordinated turn at 50 degrees. It takes 1.5 Gs to maintain a 50-degree bank turn and 1.15 Gs for a 30-degree bank turn. So I figured, well, you know, he's probably going to carry a little bit more than what he did for a standard 30-degree bank, but he's never going to pull the amount of Gs for 50 Gs. So if the pilot maintained only 1.3 Gs in the 50-degree turn, that creates a reduction of 550 feet per minute, which makes the VVI 500 feet per minute for the climb. The VVI would have shown minus 134 feet per minute at the time of the crash. This type of situation is almost always blamed on the effects of a high-pressure altitude. However, the characterization is misleading. This pilot would probably have successfully completed his turn on a calm day. He would have been 140 foot higher at the crash site than with the crash winds. Pressure altitude had nothing to do with this accident. The two main factors that are critical are calculated climb performance and wind speed. Let's take a look at the same situation, only in a no wind and one with a 20-knot wind. The pilot would have had an additional 169-foot obstacle clearance on a no-wind day, which is kind of counterintuitive. If the wind had been 20 knots instead of 14, it would have been far, far worse, as you can see from these numbers. Commencing the downwind turn at approximately 50 feet AGL was obviously a major contributor to this accident. The view from the cockpit as you are approaching the crest of a knoll at a very low altitude probably resulted in a steepening bank away from the knoll back toward the airport, which was lower terrain, and reflexes pull up, which probably resulted in a stall. The cognitive dissonances must have been extreme. You knew you could climb at over 1,000 feet per minute. The slowly rising terrain to the east would not appear to represent a problem. However, that 1,000 feet per minute rapidly deteriorates to a minus 143 feet p.m. due to the kinetic energy deficits created by the changing air mass vector relative to the direction of flight. This results in a constant need to increase ground speed to maintain climb speed. If you review the detailed flight parameters printout, by the second you see the GS steadily increases. The excess energy normally used for the climb must now be diverted to increase the ground speed of the aircraft, which results in a steadily lower VVI. What was probably screaming in the pilot's mind was, wait a minute, I should be climbing at over 1,000 feet per minute. I am now climbing at a minus 143 feet per minute while maintaining V sub x. I must be caught in a downdraft. He would be very wrong. There was no way this pilot knew that if he continued to just main V sub x, he would have maybe cleared the null. I think the VVI dissonance is what causes a pilot to raise his nose instinctively and then rapidly enter a stall, even in the absence of any obstructions in the flight path. Congratulations, you have safely experienced an almost non-recoverable departure stall accident at Lake Tahoe. Your AFM will not alert you to these kinds of situations. The largest energy deficits will occur with the strongest winds. Always use caution anytime you turn downwind quickly with a strong takeoff headwind component, have no excess energy, and are at a low altitude. While it is easy to blame this pilot because of starting the turn at 50 feet, let's look at the same situation except where the turn is started at 500 feet and with a 30-knot headwind. The cognitive dissonance is even greater in this example. The VVI goes from over 1,000 feet per minute to minus 819 feet per minute. You lose 230 feet in the turn. This is crazy. The first impression would surely be that you're caught in a major downdraft and you would raise the nose into a rapid stall and crash. The only solution if you're caught in a downdraft is to apply max power and climb at V sub x and hope for the best. However, that is exactly how the turn to downwind should have been executed. So the issue becomes one of pilot discipline. In both this case and the accident case, sticking to V sub x will result in a non-accident. This is why the approved procedure at South Lake Tahoe is to fly runway heading to the golf course and then execute a shallow banking climb back to the lake after you've gained sufficient altitude. Again, the largest energy deficits will occur with the strongest winds. Always use caution anytime you turn downwind quickly with a strong takeoff headwind component, have no excess energy, and are at a low altitude. However, the destructive psychological effect of a rapidly deteriorating VVI while at V sub x and max power should not be underestimated. We were able to calculate that the pilot would have been able to survive in both these cases if he knew what to expect in advance, but there is no predictive tool to tell the pilot what the aircraft performance will be in these types of situations. We also did not address the possibility that the pilot did not accurately maintain V sub x, or that there in fact may have been a downdraft present in the accident scenario, which would have exacerbated the climb performance further. We could fault the pilot for too excessive a bank, but a shallow bank would have extended his ground track farther east into higher sets of terrain. Accident chains are just a bunch of little things that add up to an accident. My judgment is the primary cause of this accident was clearly the high bank turn started at midfield. It was further exacerbated by the reduced climb performance caused by the wind components and energy deficits.